Hello students. So in the previous class we started with higher order linear differential equations, and where we learned methods to find out the complementary function, and we also introduced ourselves to higher order linear differential equations with non-homogeneous right hand side, and then we learned how to find out particular integral depending upon what type of functions that are given to us, right. So, what kind of right hand side we have, depending upon that we can be able to determine the particular integral. The idea behind particular integral is that if we have a homogeneous equation, then let us say y is equals to phi x is the solution or the complementary function, and then we have psi x as the solution of this non-homogeneous equation, then phi x plus psi x will be the solution of this non-homogeneous equation as well, right. So, we did give a little bit theory about calculating the particular integral. So, today I will work out several examples where so this lecture will be all about solving examples where we see depending upon what type of functions that is given on as the right hand side of the differential equation, we can determine the particular integrals, right. So, let us proceed. So, first of all, let us start with a very simple equation. So, example 1, which is of this type. So, solve the ordinary differential equation given by d square y by dx square minus of 2 dy dx plus y is equals to x square e to the power 3x e to the power 3x, right. So, let us call it equation number 1. Here we are not in particular interested to find out the particular unique solution in a way, so that we need initial conditions. So, we require two initial conditions to determine the two arbitrary constants, but we are sort of not doing that here. We are just interested in the solution of this ODE, because that part is obvious. So, the solution goes like this. Obviously, we have to consider first of all the equation with 0 right hand side, that means the homogeneous equation, to determine the complementary function. So, one more thing is that instead of having d square y by dx square, we can have y double dash or y double dot, they are all same. So, the auxiliary equation of 1 will be given by m square minus 2m plus 1. So, from here we will get m is equals to 1 actually. So, 1 is the repeated root, and therefore, the complementary function of 1 is ycx, which is given by c1 plus c2x into e to the power lambda. So, that is 1. So, e to the power x. Let us call this as equation number 2. So, complementary part is done, right. Now, we are going to find out the particular integral. So, and of course, you can write where c1 and c2 are arbitrary constant, where c1 and c2 are arbitrary constants, right. Okay. Now, the particular integral of 1 is given by, so we have yp of x equals to 1 by fd. So, in our case the fd is d square minus of 2d plus 1, and we have x square e to the power 3x, right. So, this is 1 by d minus 1 whole square x square e to the power 3x. So, this 1 by d minus 1 whole square will operate on a x square e times e to the power 3x in the following manner, that we can write. So, here we are basically using the formula of this type. So, let me write down the formula. It was 1 by f d of e to the power a x into v is equals to e to the power a x divided by f d plus a of v, where v is a function of x. So, this formula is also very well known in the particular integral type situation. So, the proof you can find in any textbook, but we are going to use this formula. So, here we have e to the power a x times v, where v is x square, right. So, we will bring e to the power 3x here, and we can write this as d plus 3 minus of 1 whole square into x square, right. So, this is what we will get. Let us go to the next page. Okay. And then this will reduce to e to the power 3x, and we will have 1 by, so I will take 2 out. So, this will become, if I take 2 out, then this will be, this will become 1 plus d by 2. So, I am taking 2 square out, whole square into x square. So, this is e to the power 3x by 4, and I will have 1 plus d by 2 to the power minus 2, right. So, this will be 1 plus d by 2 to the power minus 2 into x square. So, here you have to know the negative binomial expansion, which is not a very big problem here. So, we will write 1 minus d plus 3 by 4, or 3 d by 4, sorry, d square by 4 minus dot dot and so on x square. I am not writing the remaining terms, because after this third term, rest of the powers will become 0. So, it hardly matters if you write or not. So, here this will become e to the power 3x, and then we are charging x square. This is like an operator, this is like an operator that you are charging on x square. So, this will become x square minus d dx of, so this capital D is basically d dx. So, when you are charging on x square, it will become 2x, and this is 3 by 4 into 2 bracket close. So, this will yield e to the power 3x by 4, and I will have x square minus 2x plus 3 by 2. So, therefore, the required general solution, the required complete solution y x equals to ycx plus ypx. So, ycx is c1 plus c2x into e to the power x plus e to the power 3x by 4 x square minus 2x plus 3 by 2. If there are any sign mistakes or anything, then we can you can correct that one. Otherwise, I think it is correct. Yes. So, here we have used a particular method basically, that is, if you have the right hand side as v into e to the power ax, then we can use one of the formulas to calculate the particular integral, which I have written down, and we can have the particular integral of this type, and therefore, the complete solution will be sum of these two, and this is the required complete solution, right. Okay, let us move on to our next example. We will have, or we can have this example 2. So, solve d3y by dx cube minus 3 d square y by dx square plus 4 dy dx minus of 2y is equals to e to the power x plus cos of x. Solution. So, again let y is equals to e to the power mx be the trial solution of the homogeneous equation of the homogeneous equation to 1, right. Then the auxiliary equation, is given by m cube minus of 3m square plus 4m minus of 2 equals to 0. So, from here we can take m minus 1 out. So, there will be a factor of m minus 1 and the remaining factor can be written, so ultimately everything can be solved in terms of m, and it will be 1, then 1 plus minus I, right. So, there are 3 equations, the equation is cubic. So, there are 3 roots, one of them is real and other 2 are complex. So, complex roots occur in conjugate pairs. So, we have a 1 plus minus I. So, therefore, the complementary function corresponding to 1 is given by ycx equals to c1 e to the power x plus e to the power x into c2 cos x plus c3 sin x, where c1, c2 and c3 are arbitrary constants, right. So, up to here is the complementary function part, right. Now, we are going to find out the particular integral. Next we can write the particular integral is given by yp x equals to 1 by fd, that means d cube minus of 3d square plus 4d minus of 2 into e to the power x plus cos x. Okay. So, here we will just use the distributive property, that is d cube minus 3d square plus 4d minus of 2 of e to the power x plus 1 by d cube minus of 3d square plus 4d minus of 2 cos of x. So, we have distributed this operator on e to the power x and cos x equally. Okay. Now, this can be written as 1 by d minus 1 into d square minus of 2d plus 2 e to the power x plus 1 by d minus 1 d square minus of 2d plus 2 into cos of x. So, here we will replace d by a to the factors where it is not becoming 0. So, we have d by a, if we do, then this is d minus 1, and here it will become 1 minus 2 plus 2 e to the power x, and here basically we will substitute d square equals to minus of a square to the factors where to the terms where it is not becoming 0. So, this is d minus 1, then minus 1 minus of 2d plus 2 into cos x. So, here this will become 1 by d minus 1 e to the power x plus 1 by d minus 1, then this is 1 minus 2d, right, 1 minus 2d cos of x. Okay. So, since at d is equals to a, this first factor is becoming this 1 by d minus 1, that is becoming 0. So, we replace d by d plus a as per the rule. So, here it will become e to the power x 1 by d plus 1 minus 1 plus this will become 1 by. So, since we will get 1 d square, that d square will be again replaced by minus of a square. So this will become minus of 2 minus of 1 plus 3d minus of 1 into cos of x. So here it will become e to the power x 1 by d of basically 1 minus, here I am getting minus 2 and then I am getting minus 2 and minus 1. So plus 2 and minus 1. So this will become plus 1 by 3d plus 1 of cos of x. So again 1 by d of 1, we know that this is x, so x e to the power x, and we will multiply numerator and denominator by 3d minus 1. So this will be 3d minus 1 and 9d square minus 1 cos of x. So now I can replace, I will do the remaining calculation here. So I will replace d square equals to minus of a square. So this will become 3d minus 1 minus of 9 minus of 1 cos of x. So therefore this will become x e to the power x minus 1 by 10 3d, that means d dx of cos x will be minus of sin x. So this is minus of 3 sin x and then minus of cos x. So ultimately we will end up getting x e to the power x plus 1 by 10 3 sin x plus cos of x, right, 3 sin x plus cos of x. Therefore the required complete solution, the required complete solution is given by y x equals to ycx plus ypx. So ycx is c1 e to the power x plus c2 cos x plus c3 sin x into e to the power x plus x e to the power x plus 1 by 2 1 by 10 3 sin x plus cos x. So this is the required answer to our given third order ordinary differential equation with non-homogeneous right hand side. So in this case basically you had e to the power x plus cos x. So therefore e to the power x plus cos x you can divide in a way that e to the power x will be on the 1 by fd of e to the power x plus 1 by fd of cos x, and that is how we are determining the particular integral, right. This is one such example. We can solve, so I am looking for a fourth order example. So let us consider a fourth order equation. I hope I have it in my notes. So example 3. So solve d4 y by dx4 plus 2d square y by dx square plus y is equals to x square cos of x, right. So basically here we have a fourth order ordinary differential equation but linear, right. So and of course non-homogeneous right hand side. So you can write all these things: fourth order linear non-homogeneous ordinary differential equation. So at least this much information we can get from the ODE. So now the auxiliary equation, let us call it as equation 1. Auxiliary equation 2(1) is given by m to the power 4 plus 2m square plus 1 equals to 0. So from here we will get m square plus 1 whole square equals to m square plus 1 whole square equals to 0. So therefore from here we will get m is equals to plus minus I, right. So that means we have 4 roots and they are all complex. So that means the roots are occurring in the conjugate pair. Okay. So, therefore, the complementary function to 1 is given by yx equals to yc of x equals to we'll have c1 cos of x plus c2 sin of x, and similarly we'll have no c1 plus sorry so this will be c1 plus x c2 into cos x plus c3 plus c4x into sin x, because the roots are also repeating, right. So, I there it's twice, and minus I is also twice. So, we will have c1 plus c2x into cos x plus c3 plus c4x into sin x, right. So, this is the particular integral complementary function. Now, we will determine the particular integral, right. So, particular integral will be defined in this way. So, the is given by following, right. So, we will have yp x, which is 1 by fd, that is d to the power 4 plus 2 d square plus 1 of x square cos x. So, this will be what? This is what we have to determine. Okay. So, we have a product of two functions. So, here if you have product of x square and cos x, so we know that if one of them is exponential, then we can apply that e to the power ax into v formula, right. But here what will be the if you want to use a similar type of rule, then what will be the resulting outcome. So, we know that there is a way around it. So, what we do, we will take, let y is equals to 1 by d to the d square plus 1 whole square into x square cos x, and z equals to 1 by d square plus 1 into x square sin x. So, therefore, this will imply y plus iz equals to 1 by d square plus 1 whole square x square cos x plus x square sin x. Okay. And then this will become I plus z. No? So, there will be an I here. So, this is x square sin x. So, we will have 1 by d square plus 1 whole square, x square will be out, and we know that it will become cos x plus I sin x. So, from Euler's formula we know that cos theta plus I sin theta is e to the power I theta. So, this will become e to the power I x, right. So, this is coming from the Euler's formula. So, cos x plus I sin x, right. Okay, now it is under that e to the power ax into v category, where a is equals to I basically. So, here if I replace d by d plus I, so then what will happen? So, e to the power ix will come here, and we will replace d by d plus I whole square plus 1 whole square, and this will become x square. Okay, now if you break that d plus I, so that will be d square plus 2 di plus I square, which is minus 1, and therefore minus 1 and plus 1 will cancel out. So, this will become e to the power ix 1 by d square plus 2 d I whole square into of x square. So, this is e to the power ix, and this will become now here this here we can take d out. So, d plus 2y of x square. So this is d square, this is whole square, and then we can take 2y also out, 2y whole square out. So this will become minus of 1 by 4d square of 1 by 1 plus d by 2y whole square x square, and this will become minus of e to the power I x by 4d square, and we will have 1 plus d by 2y to the power minus 2 x square. So now we can do the binomial expansion, and this will become if we do the binomial expansion, 1 minus d by I minus 3 by 4 d square dot dot and so on of x square. So again I am not writing the higher order terms because d3 of x square is 0 and so on. So this will become minus of e to the power I x by 4. This will become 1 by d square minus 1 by I d minus of 3 by 4 3 by 4 of x square. Then this will reduce to, so I will simplify here, this will reduce to e to the power minus of I x, and here I will have a square of d square, that means we have to integrate x square twice. So this will become x to the power 4 by 12 minus of x cube by 3i and minus of 3 by 4 x square, right. So this will become e to the power I x, so 1 by 4 cos x plus I sin x, cos x plus I sin x plus x to the power 4 by 12 minus x square by 3, we will do I there, and minus 3 by 4 x to the power 2, right. So this is the required particular integral. Therefore the complete solution is given by y is equals to yc plus yp plus yp. So yp is this one and yc we have already obtained, so that value we can put here. Therefore here what we have seen, that if you are given a differential equation of higher order, and if it is x square into cos x or x cube into cos x or whatever, so then in that case instead of calculating the particular integral of 1 by fd of x square cos x, what you can do is that you can try to construct this exponential, and then we know that how does the formula work for v into e to the power x. Here a is equals to y, so we did some simplification and we obtained our required particular integral. So similarly you may have x into sin x or x into cos x, or I mean basically product of two functions, and you are needed to find out the particular integral. So basically the methodology is same, and the idea is that you first find the complementary function and then you find out the particular integral, right. So this is what I wanted to talk to you about in this lecture, and there are many examples which you can solve from your assignment sheet and as well as the textbooks that I have mentioned. So if you look into them, you will find a lot of examples to practice and to work on. So I will stop here today, and then we will continue this discussion in the next class. Thank you.